Hi, in this video I'm going to present two more proportions. Again, another excuse to talk about some algebra, ratios of proportions, that happen within the context of triangles. And so the first idea pertains to this particular situation. So we have any old triangle here. And what I'm going to do is within that triangle I'm going to create one line that's parallel to what we'll call the base, or to a side of the triangle. And so based on this particular diagram, we do have two similar triangles by angle, so these angles are congruent, corresponding angles. These are congruent, corresponding angles. So, and of course that's congruent to itself. So you have the top triangle similar to the whole triangle. So by angle. So what we can do is we can set up a proportion, because corresponding sides are proportional, blah, 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 blah. Okay, but a little nicer form of that proportion would look like this. So I'm going to call that A, and that B, and that C, and that D. Okay, so A is this length, B is this length, C is this length, and D is this length. And so this idea is called the side splitter theorem. Side splitter theorem, down, now. Side splitter theorem, down, now. And what it says is this parallel line, this blue line, so a line parallel to one side of a triangle cuts the two sides proportionally. Okay, now what does that mean? Well, what that means is this particular line that's parallel to this third side, or us side, or base of the original large red triangle, cuts this side, A to B, equal to C over D. So what we can say is that A over B equals C over D. Okay? Piece to piece equals piece to piece. This is a theorem, however, that talks about the side lengths, these four lengths, and only those four pieces. Each piece of the original triangle side that's cut by this parallel line. Okay, so here's an example. And we'll work down here, and let's say we got this little situation going on. And if that line is parallel to that line in that triangle, and let's say that this whole is 14, and let's say that this is 6 and 10. So if I were to try to find x, okay, well I need a name for this top piece, and if the whole is 14, if part of it's x, then that piece right here is what's left, 14 minus x. Okay, so now I'm going to use a side splitter theorem to set up a proportion. So 14 minus x over x, piece to piece, equals 6 over 10. Okay, and that's by the side splitter theorem. This line right here cuts these two sides proportionally. So 14 minus x over x equals 6 over 10. And again, that's brought to you by two similar triangles. What I can do now is simplify 6 over 10, because I don't feel like dealing with big numbers. That's 3 to 5, same thing. And now I'm going to solve. So I'm going to distribute the 5 to the 14 minus x. And that has to be equal to 3 times x by the means extreme property. 5 times 14 is 70 minus 5x when I distribute that 5 equals 3x. I'm going to add 5x to both sides, and that gives me x equals, when I divide both sides by 8, 70 over 8, which is a fancy way of saying 35 over 4, which is a fancy way of saying, what's that? Almost 9, so it's 8 3/4. Okay, so going back to the original diagram, this piece right here is 8 3/4, and since the whole is 14, then this is what's left, which is 14 minus 8 3/4, which is 1/4 plus another 5 1/4. Okay, so that's one example using the side splitter theorem. Another idea that has to do with proportions in triangles is what I call the angle bisector proportional theorem. Okay, and here's what the situation is here. We have any old triangle, and I'm going to create an angle bisector, okay, which makes those two congruent by definition of angle bisector. Now, what this theorem says is that this angle bisector of any triangle, okay, remember angle bisectors by definition create two congruent angles, cuts the side that it hits, right? So it'll cut this side proportionally to the other two sides. So what that means is this. So if I throw some letters in there, A and B, if I call that C and D, what that really means is as long as that's an angle bisector, then A to B equals C to D. Okay, left to right equals left to right. Of course, another way to write that would be, if you want to say left to left, you could say C over A, top to bottom, equals D over B, top to bottom. Okay, again, they're going to give you the same thing by means extreme. AD equals BC, same thing. So that said, what we have to do now is look at an example problem. So here's an example problem using that. Again, there are no, by the way, similar triangles here, just congruent angles. Okay, so here's an example. Okay, I have any old triangle. Let's bisect that angle, get a little crazy. So here's my angle bisector, which makes these angles congruent by definition. And let's say we got, I don't know, just give it some numbers, 6 and 9. And we'll call this piece 4, and we'll call that X. Alright, so by the angle bisector proportional theorem, I can set up a proportion. This angle bisector cuts this side, so 4 over X has to be equal to the same ratio as the side lengths, 6 over 9. Okay, left to right equals left to right, or you could have said 6 over 4 equals 9 over X. 6 over 4 equals 9 over X. You get the same thing, man. 6X equals 36. 6X equals 36, which makes X equal 6. Okay, and that's the angle bisector proportional theorem. So two ideas here, both involve proportions and triangles. We have the angle bisector proportional theorem. This angle bisector cuts the side, this whole side proportional to the other two sides. A over B equals C over D. And we have side splitter theorem. This line parallel to this line creates A over B equals C over D. Cuts the sides proportionally. Thanks for listening. Peace.